Hello, thank you, Phil. Actually, as you may have noticed, I've changed the title of my talk. Although I will also speak a little bit about the planet population emerging from rings. That was the original title. I should say that most of this work has been done by my student Chiara Scardoni, and in collaboration with Giovanni and Katie Clark. Um, so type 2 migration, why should we worry about type 2 migration? Well, first of all, one might think that this is, very standard theory. We all know everything about it. But actually, as somebody was saying also yesterday, maybe things are not as easy as they seem. Um, as we know that type 2 migration occurs when a planet is massive enough to open up a gap in the disk. Is this relevant to the planets or the disks that we observe? And we have evidence, plenty of evidence for the presence of gaps in disks. And it's now compulsory to show the D-sharp sample. Although one should notice that all these gaps here are dust gaps and not gas gaps. Type 2 migration occurs when there is a gap in the gas. And usually this figure here is used to say how common these ring systems are. It should be noticed that this particular sample is very biased. It was selected in such a way to select the systems that we know already have rings. So if one really wants to say something about the occurrence of these ring systems, one should try and have an unbiased sample, and that is why I prefer the Long et al. Torus sample here. This is a sample of 32 disks observed in Torus, and 8 of them are in binaries, 12 are single stars and do not show substructures, and 12 are single stars and do show rings. And so from here we can have an idea of what's the incidence of rings in these disks. So it's 50% of the single stars have got rings, and this number goes down to 37% for the whole sample. So yes, indeed, based on this, we can see that that these ring structures are quite common. What's the origin of the rings? Obviously, this has been debated somewhat. Actually, one other thing that is interesting coming out of the Long et al. And also from the D-sharp sample is that the location of the rings doesn't appear to coincide or to be correlated with the expected location of snow lines, which actually kind of rules out snow lines as the origin for rings. And we all know that we prefer to explain this in terms of planets. And there are some cases where we know that there is a planet in the ring. So that's the case of PDS 70, where we have a planet that sits nicely in the middle of a ring shown in the ALMA image. So actually, I think all of this is telling us that when we observe these structures with ALMA, we do not really see planet formation, but what we see is planet disk interaction. These are not planet forming disks; these are planet hosting disks. Okay, so can we push this further and try and say something about the overall population of planets that would emerge if we assume that all these rings are actually due to planets? What can we say about it? And this is the aim of the compilation that I've done recently. This plot was already shown a couple of times yesterday. What I've done here is to take all the rings that we know from the Taurus sample, from the D-sharp sample, and these are archival rings that we know. And then for each of them, basically, we could run hydrodynamical simulations and try to infer what are the properties of the planets that would produce this kind of gaps. But this would be very time consuming because this sample is actually now quite large. It's 50 rings, more or less. And rather what we've done is to just assume a simple scaling of the gap properties with respect to the planet parameters. And in particular, here I assume that the width of the gap is just a constant times the Hill radius of the planet, where this constant is calibrated on the few cases that we know in the long sample, that in the long et al. Sample that do have numerical simulations, hydrodynamical simulations to explain the gaps. In particular, there are two systems here. One is CI Tauri, for which Kati has done some modeling, and WC480, for which we have done some modeling ourselves. And just to show you here how is this modeling done, this is in Liu et al. This is the ALM observation of MWC480. We have done some RedMC 3D modeling to derive the millimeter dust distribution, and then some numerical simulation using Phantom and then SPH code. So that's the gas surface density and the dust surface density, and then we can compare the millimeter dust profile coming from the observations to that coming from the simulation, and this is the comparison. Here is so the dotted line is from the observation, and the dashed line is from the simulation. And here just show also the scaled version of the gas profile, which shows that actually this particular planet doesn't open up a gap in the gas, but only in the dust. And in the end, for this particular object, it turns out that the planet mass is such that the width of the gap is roughly 4 times the Hill radius. And similar results also can be obtained for example, for CI Tauri that was modeled by Kati. So we take a number which is of the order of 5 as a scaling factor between width of the gap and Hill radius of the planet. So we do that for all the gaps that we know, and this is how we come with all these mass estimates here. And so this is where these planets, these purported planets would sit in this plot of mass versus semi-major axis. Now, this plot here, I think, is interesting in many respects. First of all, we notice that the planets sit here in a region which is not accessible by any other detection technique. They are too far to be observed by radial velocity, and they are too well, not massive enough to be observed directly, except maybe for really the tip of the iceberg here. And indeed, in these few cases that have a very high mass, we do observe them. This object here is PDS 70 indeed. If one asks why don't we see actually the planets in these gaps, well, that's because they are not massive enough to observe them. The other thing which is interesting about this plot is that these planets here occupy a region in the parameter space which is very hard to explain by essentially all of the planet formation mechanisms that we know, because gravitational instability would form planets up there with masses much higher and separation much wider, and at the same time, core accretion would at 1 mega year, because you have to remember that these objects have an age of roughly 1 mega year. So core accretion would produce planets that sit more or less in this region here. So none of them would produce this kind of objects here. So it's a bit hard to explain how do they form. And one possibility that was also mentioned yesterday by Kati is that we can form rapidly the cores of this planet, for example, by a mechanism that was proposed by myself and Ken Rice a few years ago here. If we look at the very early phase of disk evolution, where the disk is supposed to be self-gravitating, we know that the spiral structure in the gas can efficiently trap solids, and this is quite efficient in trapping solids, so that the solid component can collapse and directly form some solid cores. The masses of these cores from Rice et al. Are very large, of the order of the mass of the Earth. Now, I wouldn't trust particularly this specific number, because back then we didn't have much resolution, and so I think also given the new evidences, it's time to reevaluate this number here for what kind of cores do we expect based on this mechanism. But this is not the whole story. We can do something more. What I think is nice about this kind of plot is that really, by comparing the location of the planets when they are just born to the one that they have when they are grown up, we can say a lot about the evolution of planets from here to there. I think, comparing, we know that if they're born here and then they evolve there, I mean, this relative location can be used as a way to test our models for the evolution of planets. And this is also what we have done in this paper here. We have again assumed a very, very simple model. We have considered that if the planets are below the CRIDA criterion for gas gap opening, we assume that they migrate according to type 1 migration and accrete. And then once they reach the gas gap opening mass, they stop accreting and they continue migrating with type 2 migration. And if we do this exercise, we take them from here and we evolve them for 3 to 5 mega years, they end up more or less in this region here, which is nice because basically they end up in the region where we do find the planets nowadays, well, around evolved stars. So this makes it plausible that these early planets then evolve to become the planet population that we see today. However, not everything works well. We can actually check also the occurrence rates of planets. If we take this, the only sample that can be used to check for this, the occurrence rate is the Long et al. Because it's the only unbiased sample of rings that we have. And the occurrence rates of planets in this case would be in the range of, say, 30% roughly. And this can be compared with the one that we know from planet detection. I don't know much about it, so I take the numbers from a recent paper by Fernandez et al. And then in which they suggest that the occurrence rate of giant planets is of the order of 26% for planet masses above 0.1 Jupiter. On the one hand, this is nice because it's comparable with the 30% that we get, but the problem is that this is for planets above 0.1 Jupiter. All of our planets are above 1 Jupiter, and Fernandez et al. Say that if we raise this number to 1, I mean, the occurrence rate drops significantly, so it's not obvious that these numbers actually work out well. So all of this is to say that, from going from here to there, we need to know exactly how do they migrate and what is the rate of type 2 migration, which is the most important migration in this case. So as I was saying before, we know everything about type 2 migration, don't we? This is, as I was saying, very well known. In this case here, the planet opens up a gap in the disk, and it's very easy to determine the migration rate just balancing torques. This is the angular momentum lost by the planet. This is the angular momentum lost by the gas at the planet position. This is the viscous torque. So you can solve this equation to get the rate of type 2 migration, which is shown here. And we can see that this is made of two contributions. One is this 3/2 nu over radius, which is the viscous velocity, multiplied by this factor here, b over b plus 1, where b is the ratio of, say, the local disk mass with to the planet mass. And when b is very large, so when the disk is massive, the migration rate is the viscous rate, and the planet really behaves as a fluid element in the disk. This is an example of a 1D diffusion code that was actually Marco Tazzari's master's thesis. Here the B initially was very large, and indeed the planet migrates as a fluid element in the disk. If B becomes small, the migration rate declines, becomes smaller than the viscous rate, and this material, is banks up upstream of the planet position, creating a steepening of the surface density behind the planet, and an emptying out of the inner disk. This is all well known. Siren Clark and Ivanov et al. Several years ago have worked this out in detail. One important thing about this model here is that a fundamental assumption is that there is no gas that is able to cross the gap. So really the planet divides the disk into two, and there is no communication between the outer part and the inner part. Recently, a few studies have challenged this, in particular two papers, Duffel et al. And Darman and Clay, have noticed that, well, I've run 2D numerical simulations of the problem. Duffel et al. Used their Disco code, and Darman and Clay used Nirvana. And these are the results of these two papers. This is the migration rate as a function of disk mass. And I should say I don't particularly like these plots, because they show here the ratio of the migration rate to the viscous rate. Okay, the viscous rate is just the one without accounting for the inertia of the planet, this B term that I mentioned yesterday. And if you look at this plot, for example, up here, and read the paper, they would say, one is, this ratio here should be 1. That's the canonical type 2 migration. And based on this, you can see that the actual migration rate it can be higher or smaller, larger or smaller than the predicted rate. Actually, this is not really true, because this does not take into account the fact that we know that when the disk mass is small, indeed, type 2 migration should be reduced. And if you plot if you superimpose to this plot the real expectation for type 2 migration, this is the kind of plot that you would have. And so basically what you see is that the results of Derman and Clay, and also of Duffel et al., essentially measure a migration rate that is always faster than the type 2 at any value of the disk mass. Maybe the discrepancy is larger here, and it's smaller disk mass, but still the migration rate that they measure is always above the one that is predicted by type 2 migration. And Derman and Clay did it for a number of disk masses. Duffel et al. Also checked how this varies with h over r. And it's interesting to notice, although I don't understand very well this plot, that if you decrease h over r, the migration rate decreases. Obviously, what is the origin of this, and of this discrepancy? Clearly, this must be due to material crossing the gap. In particular, if there is some gas that moves out of the planetary orbit, it can take out more angular momentum and allow a faster migration of the planet. I should say that all these plots, all these simulations have been run for not much than 1,000 orbits, even less than that. Which is only 0.05 viscous timescales for this particular choice of parameters. So what we've decided to do is to redo these calculations to understand a bit better. And in particular, what we want to check is the dependency on h over r. And the reason behind that is because we know that if we decrease h over r, basically we expect less material crossing the gap. We expect to have a deeper gap, less material crossing the gap, and therefore we should recover the standard type 2 migration. That was the aim of this exercise. We use Fargo 3D in 2D. That's an example of the density profile as a function of radius at various times during the simulation. But here, let me go directly to the main result of our of this work, which is to measure the migration rate, and this is what we get. So here I'm plotting the measured migration rate of the planet as divided by the actual type 2 migration, not the viscous rate, the actual type 2, including the reduction due to the planetary inertia. This is as a function of time. In units, I don't know if you can read at the bottom, and this is in units of the viscous time at the initial location of the planet. These are the various simulations that we have run for varying h over r, and also for varying these masses. And h over r increases in this direction here. And so we can already see a number of things out of this plot. First of all, as expected, well, in some sense, we recovered the fact that the migration rate is faster than the standard type 2 rate, at least initially. We also noticed that if we decrease h over r, the migration rate gets smaller, which is again something that I would expect based on what I said before. There is less mass flow through the gap. But the most important thing is that if you wait long enough, and long enough is not that long, 0.1 viscous timescale, you see that the migration rate actually drops exactly to the value of the standard type 2 rate. So basically, what I can conclude out of that is that this fast migration is just a transient. It's a transient that doesn't even last for much long in terms of the evolution of the planet. Okay. And actually, this can be confirmed also in some other ways. For example, here we check whether the migration rate depends on the disk mass. This is one of the conclusions of Darman and Klein and Duffel et al. So if you change the disk mass by fixing all the other parameters, then the migration rate changes, and actually it doesn't. More or less, the two curves are very close to each other, and they both eventually reach the standard type 2 rate. However, I should say that here the differences in this mass are not very large. It's just a factor of 1.5 between these two simulations. So I think it's worth exploring this a bit more. Just another thing to check is the evolution of the parameter B. We initially start from a very massive disk where B is 30, 20 to 30. Obviously, as the planet migrates, this value decreases, and eventually migration slows down. Finally, we can check how much mass flow there is through the gap. Again, this is a plot from Derman and Clyde. This is the region very close to the planet. You see, this is in units of h. This is the region very close to the planet, and indeed, at different times, Derman and Clyde measured an outflow, well, a mass flowing out of the planet of the planetary orbit, which was their explanation for the faster migration. We do see exactly the same behavior, but as you can see, as time goes by, this mass flow decreases, and we can plot it as a function of time. This is for two different simulations. Initially, we have some mass flowing out of the gap, consistent with the faster migration, but very rapidly this reaches zero. So when there is no more mass flux to the gap, sure enough, the planet migrates as it should do. So here I think I'm done with time. So let me go to my final conclusions. I would say that the observed these gaps hint at the fact that planets might be undergoing type 2 migration because they open gaps in their disk as early as after 1 mega years of the formation of the star. And I think that it's very important to compare the properties of planets this exercise that I've done, I think is very useful to compare the properties of planets emerging from the gaps with the properties of evolved planets to assess how the planets change during their teenage from when they're just born to when they're grown up. An important question to ask is, because type 2 migration occurs in these massive cases, whether type 2 migration is locked to the viscous rate. Duffel et al. And Darman and Clyde would say no. I would say yes. Well, there is a fast migration, but this is just transient that only lasts for a very short time. After 0.1 viscous time, the migration rate attains the normal value from type 2 migration. Well, there is something else to be discussed. Especially, I need to understand a bit better the role of disk mass. We only probed very small variation in disk masses. It's important to check whether, with a large range of disk masses, the result stands. But overall, I guess this is more or less what I wanted to say. So, thank you.
Gap, or is it a gap with vortices and such showing up
No,
the
it's
edge?
smooth.
It's smooth. So what's the viscosity you're using?
It's 5 times 10 to the minus 3.
Okay. So and the other question, if you go back, sorry, that plot you were just on with the trajectories. Trajectories.
Yeah.
Sorry, that one.
This one.
No, sorry, back. That
This
one.
one.
Right. So at the end, those planets are slowing down again once they get down to the.
Here you mean this?
Yeah, and then you stop the run. So what
well,
actually
this is the
happened
boundary effect. This is where the planets
Okay.
have reached the inner edge of the
Okay.
of the grid. So this behavior here, right, is just a numerical effect because
Okay.
we have reached the inner
That's
boundary
what
of the
it
disk.
is. Okay.
So we've seen models that a single planet can make multiple gaps. I'm wondering if a lot of these apparent low mass planets might actually just be secondary gaps from higher mass planets buried in the disk.
Even in the first part of the talk.
Yes, exactly.
It could be the case.
And that would get rid of some of these anomalous large radius low mass planets.
Anomalous large radius, low mass.
The
Well,
ones
okay.
that nobody else can form.
Yeah. Well, yes, could be. I think we need to well, obviously to do that we need to do numerical simulations of each system and check whether the parameters work out well. So
Okay.
yes, there is a possibility.
Good.
Yeah.
Is this on? Yeah. So I just wanted to ask you about your initial conditions because I assume that in order to kind of get the gap opening, you fix the planet's orbit to start off with.
Yep.
How do you do that for all the different disk masses, etc.? Because and I guess different planet masses as well, just because you'll then have different amounts of gas in the gap, which can then affect your migration. Right?
Well, first of all, in this migration simulations, we only use one single planet mass.
Okay. Right.
The process of setting it up is very long. It's basically we follow the same route of Darman and Cly. So we initially set up a disk in a steady state with no planet. It takes a long time to set it up. Then we put a planet on a fixed orbit to let it carve a gap, and wait until we again see a steady state with mass flowing through the gap at a steady state, and then we let it go.
Okay. Right.
Similar question. So how would we, when we interpret all these gaps as planets, it seems to me, I'm sure, right, some of them probably are due to planets, but I guess planet formation also has to happen at some stage, and we have seen that the planet formation process, before you have a fully grown planet, can make gaps. Do you think there is a way, given what we know, that we can distinguish from theory between which gaps may really be due to planets and which ones may be more a signature of planet formation, instead of just assuming that all of them have to be
When you say a
planets?
signature of planet formation but not be due to planets?
Well, it's been proposed, right? Like dust rings, they're like, so they can give you a very similar structure. Or that one planet carves several gaps.
I think obviously there are.
So I think I think it would be, I'm interested if there's an angle to disentangle that, or we have to rely on the observers to tell us which ones is just structure because you're in the early stages of planet formation, collecting dust and traps, forming planetesimals, rather than having a full-grown planet.
I think, of course, well, from my perspective, what I would say is that we need very detailed hydrodynamical modeling of each. If you really want to be sure that each system does host a planet, well, sure. If you want to be more convinced that each system does host one planet or two planets or whatever, you need to really run a numerical simulation, a hydrodynamical simulation that reproduces the shape of the gap and not just the width, but the overall shape of the gap. And in this case, you could be more convinced that that indeed there is a planet. Obviously, there always are other possibilities. It's interesting to see that some of the possibilities that were discussed in the past, like snow lines, are disappearing now, leaving planet gaps as a likely explanation. But what I would do is to really go deeper and do a hydrodynamical simulation of each one of the system, really, if you want to be convinced.
So when you use this width proportional to the Hill radius, you said you calibrate this to numerical simulations. Which planet masses are these numerical simulations?
Typical are Jupiter, say MWC 480 was 2 Jupiter masses. The CI Thyri one were a fraction of Jupiter.
Okay, but then use the scaling to infer masses which are an order of magnitude lower than this mass.
Yes, that's true.
Right.
Yeah, I agree.
Is there any physical reason to believe that it's still proportional to the Hill
Well,
radius?
there are theories. I think Giovanni Rossotti has a paper where he proposed the scaling of that indeed the width of the gap in the dust should scale with radius with the Hill radius exactly in that way even for lower disk masses.
Okay, I'm familiar with other theories that link the width of the dust gap to the width of the gas gap, which predict a somewhat different scaling. It's also proportional to the mass, but with a different power law.
Yes.
this might change.
Well, this depends also to the degree of coupling between the dust and the gas, because
Right.
you know, for Stokes number that are very small, maybe yes,
Mhm.
but as you go up in Stokes number, the dust becomes more decoupled, so it cares a bit less on about what the gas is doing. And in this case, you know, for millimeter size, you know, probably in the regime where Stokes number is high enough that it shouldn't. But yes, it's something to explore.
Thanks.
So regarding the type 2 results, they were very interesting. So I was wondering what your thoughts are on the recent paper by, I think last year, Robert et al. So it's the Nice group with Crida and Morbidelli on there, where they say, well, they conclude that indeed type 2 migration is proportional, is related to the viscous timescale, as I think it should be. But they said it can't be that quite exactly the same, because you carve a gap that may not be in equilibrium. The outside may be slightly different from the inside. So there is a net torque on the planet, but if the planet's going to migrate according to that torque, if it's really far away from the viscous rate, then it will move away from the outer edge.
This is exactly the origin of you know, why we wanted to do this simulation. Is because we were, you know, doing exactly this kind of argument. It can be so different exactly because of this. And regarding the fact that how do I go behind? Okay. And regarding to the fact that the gap is actually not a boundary condition, you know, just an infinitesimally thin gap, but it's got a width. Yes, we do see it here. Actually, I didn't comment much on this plot here. So basically, what I've done is initially I was saying maybe it's not exactly the viscous rate, but it's close to it, as you were suggesting. And what I've done is to check at what location in the disk the gas flow rate equals the measured value of the planet velocity. So these are the various points here, you know, with the corresponding color, are the location in the disk that for which the gas has got the same velocity of the planet. And indeed, you can see that more or less, as the planet evolves, this is kind of constant to, you know, with a factor of 2 times the 2.5 or so times the location of the planet. So basically, the planet does move with the velocity that is very close to the velocity of the gas, you know, a bit upstream of it. That's where more or less the edge of the gap is. So this probably goes in the direction that you were saying.
Okay, thank you very much.
Thank you.